Hey everyone, it's Alice here from Top Mark Science, and today we'll be looking at squashing and stretching. Throughout this video, we'll be exploring the difference between squashing and stretching, the definition of the term extension, and the relationship between force and extension. Let's get started. There will be many objects in your everyday life that you use that stretch, and they will be elastic. Pause the video here and have a quick think about what it means if something is elastic. Elastic means that we can stretch, bend, twist, and compress something. It can be elastically deformed and go back to its original shape. We can stretch and squash them, and they will return to their original shape. Other things get permanently deformed when a force is applied to them. They are not elastic. Take this catapult, for example. We can apply a force to change the shape of it. We need to apply more than one force in opposite directions. One force at one point provides the support and moves the catapult in one direction, and a force up here pulls in this direction to allow the band to stretch and change shape, and in the process the band extends, then goes back to its original shape, unless it's stretched too far and the band breaks. You may have seen those rubber lizard toys. They can be around 10 centimeters in length, but if we apply a force from its head, from its tail, to 15 centimeters, what is its extension? Well, it was 10 centimeters, then stretched to 15 centimeters, so it gained 5 centimeters of length. In other words, it's extended by 5 centimeters. Now we can test the effect of force on extension on elastic objects. We'll take a quick recap on variables before we start so the rest becomes easier. So our independent variable is the thing I change. The dependent variable is the thing that will be measured as a result of the independent variable changing. And our control variable is the thing I keep the same because it could influence our results otherwise. So our question of this experiment is what happens to the extension of a spring as you increase the force applied to it? I will go through the setup and demonstration before we think about this more. So firstly, we can set up a retort stand with a spring attached at the end and safely clamped in. A ruler, straight and in line with my spring, so I can accurately measure its unloaded length. In this case, this spring without any masses on it is 20 millimeters. It's important I record this unloaded length in my results table before moving on. Now I'm going to hang 100 grams on the end of the spring. Then use my ruler to measure the new length of the spring and record this result in my results table. Then I will add another 100 grams onto my spring, so I now have a total mass of 200 grams on my spring. This is 2 newtons. Measure and record the new length, and repeat until I have 500 grams on the end of my spring. Pause the video here and write down a basic plan to this investigation, including variables and a prediction. If you finish, try the challenge. Let's see how we got on then. Firstly, our independent variable, the thing that we are changing, will be the force. Although we're adding masses, this is just a step to help convert it into force. Our dependent variable is the extension of the spring. Although we are directly measuring the length of the spring, the aim is to use this to calculate the extension. So really, this is our true dependent variable. And our main control variable should be the spring that we use. Springs can vary in how stiff they are, and this can affect the force extension relationship. So I will use the same spring throughout the experiment. Your prediction might be different, but I could say that as the force on the spring increases, the spring will get longer. We'll talk about this in detail later on. If you tried the challenge, excellent job. A results table needs at least 2 sections. with your independent on your left and dependent variable on your right. In this case, we will be directly changing mass to convert it into force in newtons. So on my left, I will have mass, then a column for my calculated force. And on the right, our stretch length with the spring has been loaded, and a column to calculate extension in millimeters. Copy this down if you don't already have it. Then I think we're ready to complete the investigation and record our results to see what happens. Fill in the results table as we go. Firstly, we set up our equipment like so. A retort stand with my unloaded spring safely attached with clamps. Next, I use my ruler to line up to my spring as closely as possible to ensure accuracy and measure the length of my unloaded spring and record in my results table. So with 0 grams of mass on the end of my spring's length is 20 millimeters. This is what I will refer to as my unloaded length. And there is 0 millimeters of extension as it has not yet been loaded with any force. Next, I will hang 100 grams of mass on the end of my spring. Then use my ruler to measure and record the mass in my results table like so. So with 100 grams of mass, my spring stretched to 25 millimeters. Now a quick side note, although we're adding 100 grams of mass, we need to convert this to kilograms for calculations later. So we know that 1 kilogram is the same as 1,000 grams. If I want to convert kilograms to grams, I multiply by 1,000. So if I want to go from grams to kilograms, I divide by 1,000. In my case, I have added a small 100 gram mass onto my spring, and I want to convert it into kilograms, so I need to divide it by 1,000, which gives me 0.1. Okay, moving on. Now I'll add another 100 grams onto my stretched spring. So I now have 200 grams, or 0.2 kilograms of mass on the end of my spring. I'm going to measure and record, and then repeat for 300 grams, 400 grams, and finally 500 grams, or 0.5 kilograms. Now that we have collected results from our experiment, it's time to analyse them. Pause the video here to calculate the force and extension columns. Use the prompts provided to help you fill in the gaps. And if you finish, try the challenge. Let's see how we all got on. Annotate your work and fill it in as we go so you can use the results later on. So firstly, I will start with the force column. We've already been told at the top that force is calculated by multiplying the mass by 10. This gives us weight, which is a force as the result of gravity acting on the mass of an object. So when I've added 0 kilograms of mass and multiply this by 10, this is 0 newtons. Then I repeat for 0.1 kilograms times by 10 equals 1 newtons of force. Then again the same for 0.2 kilograms times by 10 for 2 newtons of force. And continuing this calculation should then result in 3, 4 and 5 newtons. So well done if you got these. If you didn't, don't worry and fill them in now. Okay, moving on to our extension column where we've already had some examples provided. Remember, extension is just the difference between the original and the unloaded length and the stretched length. So we'll be comparing everything to the length of when there was 0 kilograms of mass on the spring, which is 20 millimeters. So when we added 0.1 kilograms, it stretched from 20 to 25 millimeters, an extension of 5 millimeters. 0.2 kilograms stretched to 30 millimeters, which calculating the difference from the unloaded length of 20 millimeters gives us an extension of 10 millimeters. And repeat for the others to give us extensions of 15, 20 and 26 millimeters. By the way, the SI unit here should be converted into meters technically. However, this would give us some really tiny numbers. So today we'll be working in millimeters to make it less complicated. Cool. Now we have our two columns of interest because we're using these to plot our graph. In nearly all graphs you come across in science, the independent always goes on the x-axis and dependent always goes on the y. For this experiment, we switch them round because it makes it easier to complete more complex calculations that we won't dive into this video. So we should have force on the y, which goes up, y to the sky, an extension on the x-axis because it's across, and x goes across. Next, I need an appropriate scale that will allow me to use over 50% of my space with evenly spaced scales too. I accurately plot my points and draw a line of best fit. Hang on, there's something here that doesn't quite fit the pattern like the others. Okay, so this graph should look like this. Pause the video here and use the graph displayed to describe the relationship between force and extension. In other words, tell the story of the line using the words force and extension in your description. If you finish, try the challenge. Let's see what we came up with then. Feel free to write notes as we go. So this graph shows that as the force increases, the extension also increases. We call this a directly proportional relationship. We can see this from the straight line through the origin here, until we reach a force of 5 newtons, where it no longer follows this line and extension is no longer proportional to force. Basically, if we continued this experiment, the line would level off like so. This point is called the limit of proportionality. The clue is in the word. We have reached the limit where the relationship is no longer increasing with each other. They are no longer proportional. Here we've gone beyond the elastic limit. So the spring has become permanently deformed. It does not spring back to its original shape. This is known as Hooke's law, which states that the extension of an object is directly proportional to the force applied to it, unless the elastic limit has been exceeded. In other words, if I stretch my spring, it will always go back to its original shape, unless I stretch it too much, with too much force, in which case it will be stretched forever, and it will no longer be elastic. Okay, quiz time, guys. A lot has been covered, so let's see what we have learned today. Question 1. Objects such as bands and springs are described to be elastic. Nice work. Question 2. We can stretch, twist, and compress elastic objects, but what key feature makes them elastic? They go back to their original shape. Well done. Question 3. True or false? The extension is just the stretched length. Take away the original length. This is true. Question 4. When force on a spring increases, the extension increases too, shown by a straight line through the origin on a graph. What word can we use to describe this relationship? Directly proportional. Tricky one, but this word crops up all across science, so it's a good idea to learn it. Question 5. When we load too much force onto a spring, we can exceed the something something. As a result, the spring becomes permanently deformed. What two words fill this gap? The elastic limit. Great job if you remembered this one. Before finishing, take some time now to reflect on what you feel confident on and what you feel like you need some more practice on. Thank you so much for watching this video, guys. If you enjoyed it and would like to see more from Top Mark Science, you can like this video and subscribe to this channel. I'll see you next time.